Hello, my name is Elsa Lawrence, and today I'm going to be going over Aqueous Ionic Equilibrium Exam 3, question 18, which is part B of the Explain It to Me One More Time question. So here's that question. A 250 milliliter solution of buffer with pH of 4.37 made from 0.2 molar acid and 0.8 molar conjugate base must be a formic acid buffer. Adding 2.5 grams of potassium hydroxide to this buffer has a pH of 5.43. And we are going to demonstrate that both of these things are true. So we're going to solve this problem in three parts. First, we are going to prove that it's formic acid using our molar amounts and our pH. Then we're going to figure out the new molar amounts of base and acid after the addition of potassium hydroxide. And then we're going to plug our new molar values into the Henderson-Hasselbalch equation to solve for the pH post-addition. So first, we're taking our Henderson-Hasselbalch equation and plugging in the pH that we're given, and we're solving for pKa. And we are given the two molar values, which we'll plug in for base and acid, respectively, acid and base. So when you do this math through, you're going to get that the Ka is 1.71 times 10 to the minus 4th, which matches the Ka that we were given on our sheet for formic acid. So there you've proved that it's formic acid. Then you're going to do figure out your new molar amounts or number of moles that you have of each part of the equation after the addition of that 2.5 grams of potassium hydroxide. So you're going to take your molar amounts, which are moles over liters, and multiply by liters for your base and your acid to get your number of moles. And then for your moles of potassium hydroxide, you're going to take your 2.5 grams and do dimensional analysis with molar mass to get the 4.46 times 10 to the minus 2 moles of potassium hydroxide. Then, using those amounts that you've just calculated, you're going to take for your acid, you take your moles and you subtract the moles of strong base because base will neutralize the acid, and then you'll get your new amount as 5.4 times 10 to the minus 3 moles, and you put that over your same liters so that you will get a molar value that you can use for your acid in the Henderson-Hasselbalch equation. And you're taking that original and then figuring out how many moles you have left. And you're going to do the same thing for the conjugate base. You take the 0.2 moles of base and add the KOH, because now you're doing base and base. You'll be adding, and you'll get 0.245 moles per 0.250 liters to get your molar amount for your conjugate base. So now you have the two molar amounts for acid and base, and you're going to use that and your pKa of formic acid to plug back into the Henderson-Hasselbalch equation. So you have pH equals negative log of 1.7 times 10 to the minus 4 plus log of 0.97 molar over 0.0216 molar. And when you solve that through, you're going to get a pH of 5.43. So if we go back up to the equation above, we'll see that we got the same pH as in the equation. Let's just go back up, and there you have the 5.43 pH. So now we've proved that this is a formic acid buffer. Then we calculated our new molar amounts after the addition of potassium hydroxide to plug in so that we could prove that the buffer has a pH of 5.43 afterwards. Thank you so much. This was Exam 3, question 18, calculating the pH before and after titration of a strong acid.